Hey all, welcome to my mini teaching. This is Ryan Anderson, and today I'm talking about Simpson's paradox. Our objectives today are to describe how Simpson's paradox arises in data and then understand its connection to causal inference. Let's start with Edward Simpson, who came up with it in a 1951 paper. He was a Bletchley Park cryptographer with Alan Turing, which is pretty cool, and then got his PhD at Cambridge. So really one of these blue blood English mathematicians or statisticians, PhD, Cambridge stats. So the setup in his 1951 paper contains the paradox, and it has to do with patients receiving or not receiving a drug, and then their later recovery rates. And then we'll see from there how the paradox arises. But really quick, let me take down some data for us here. So drug versus no drug in terms of recovery, and I'll write this as D, ND, and then we'll separate this out by men and women, and that will be sort of important for the overall experiment. So 0.93 recovered for men with the drug, 0.87, 0.73, and 0.69. So that all looks well and good. Well, let's look at the totals. We have 0.78 and 0.83. So this is Simpson's paradox illustrated really well, right? The difference lies in what happens at the sample-wide level in the totals here as compared to the subpopulations here and here. Overall, you would be led to conclude that not taking the drug led to a higher chance of recovering from the disease, right? As in 83% of patients who did not take the drug recovered. However, if you break it down on either of the subpopulation levels, both for women and for men, as genders individually, taking the drug was associated with a higher chance of recovering from the disease. It's a simple Simpson's paradox, to state more generally, is in reference to any situation where across a sample, the association that we find in the data is reversed for any subpopulation. And so we can sort of take a look at why this arises with reference to the law of total probability, right? And here we're going to look at some conditional probabilities, but here, the problem is the P of recovery, P of R, given drug, is less than P of R given no drug, right? But if you look at it individually, let's condition once more on gender. So P of R given D and M is, of course, greater than P of R, P of R given ND, M, and P of R given D woman is, of course, greater than P of R given no drug woman. So that is seemingly at odds with what the law of total probability would tell us about the way we can rewrite this red expression, right? Because we know that we can rewrite P of R given D by conditioning on gender once more, right? So P of R given D should split out along men and women into P of R given D times P of drug and man plus P of R given drug women times the P of drug and woman. So how do we resolve this? If we think about it carefully, right, like the problem's going to arise in terms of these additional components of the total probability, which, I sort of like to call the weights that we're applying to these experimental expressions here, right? Because we can observe these directly in the data, the probability of recovery given drug and gender, but the crux is going to lie in the interaction between drug and gender alone. And in fact, we'll note that here, and this is sort of the ticket, right? So the interaction of taking the drug itself and gender is the key. And so, you might note from this data, right? So suppose with me for a second that like there's something inherent about men that makes them both more likely to recover from the disease and less likely to take the drug, right? And so say that it's, more testosterone just makes you do that, which might be far-fetched, but that could be something that arises here. And this sort of thing can arise in really any sort of collection of data with subpopulations like this. It's not at all restricted to gender. This can happen for age or state or climate or something like that. But it's something about inherent to the subpopulation you've chosen for this experiment that is confounding the results of our analysis. And so here's where we get into the application to causal inference, right? Where I'll say really briefly, but causal inference is a sub-branch of statistics that studies the ways in which we can conclude truly causal effects from investigating a data set and not just the associational or correlational properties, right? So we're led to sort of causally understand here there's something more going on that we're not getting at, right? So maybe being a man is a common cause for both drug taking and gender. And at any rate, I hope this is a useful introduction to the world of Simpson's paradox and what it sort of leads us to understand about data sets or be more careful in our analysis.